Hello friends, you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, today I'll show CFD analysis through a surface condenser. Actually, surface condenser is used in power plants. Exhaust hot water from turbine is actually utilized to convert fresh cold water to heated water. So here in this case we'll show the complete detailed analysis of surface condenser. Actually, from turbine, hot water will be coming out, and that hot water is entering from this inlet of surface condenser, and this is the inlet of fresh cold water. For understanding the geometry in a better way, let us have a segmented view of this model. Let us cut it from specific plane. We're cutting it from here. You can see these are the tubes through which cold water will be passing, and inside this one it is having one barrier. That means from here we'll be providing cold water, cold fresh water, and it will be passing through these openings, and at the end of this surface condenser it will be bent in the form of a U-tube, and again it will be coming out in this way. First of all, it will be going through this way in the forward direction, then at the end it will be coming back in this way, right? And if you cut it from some other planes, let us cut it from different planes. You can see here, this is the barrier. Cold water will be passing through these small tubes, and at the end it will be coming down, and finally it will come down from this opening, right? And surrounding these small tubes, hot exhaust from turbine will be coming out, and it will be hitting this cold fresh water, right? So again I'll repeat, cold water will be passing through these small tubes, and at this end it will be bent in the form of a U-tube, and finally it will come down and is coming out from this opening, right? So here is some kind of barrier, horizontal barrier is there, right? Okay, you can cut it from different planes also, and you can understand this. Let us cut it from this plane. You can see here, like from here you can understand very clearly. Cold water will be passing from here, and it will be passing to these small U-tubes, and finally again at the end it will be bent, and it is coming out from this opening. So this is the opening of cold fresh water, and this is the exit of cold fresh water, and this is the entry of exhaust from turbine, and from this exhaust we will be providing hot water at 100 degrees centigrade, and this is the exhaust. This exhaust water will be utilized to heat this fresh water which is coming from this inlet, right? And we're having two exits for hot water. This is the exhaust 1 for hot water, and this is the exhaust 2 for hot water, right? So geometry is clearly understood. Mainly in this analysis we have to find out the temperature at different exits. You have to find out temperature at the exit of cold water, and you have to find out the exit of hot waters also at two different locations, here and here, right? Okay, and here in this case we'll utilize CFD heat transfer analysis using ANSYS Fluent fault tolerant meshing, which is new to ANSYS Fluent 2021 version. Okay, for starting this Fluent fault tolerant meshing, we need to save this model as FM database or with the extension of FMD. Let us save this one with FM database. For starting a Fluent fault tolerant meshing, we need to start Fluent launcher. Let us start Fluent launcher from here. First of all, we need to open Fluent fault tolerant meshing from here. Next to that, we need to import that model from here. We need to load that object with custom setting on. Next to that, we need to drag that component into meshing model. Then with the advanced setting on, we need to import different components or parts separately. We need to copy settings to child objects, and then finally we need to create meshing objects. You can see this is the model, right? Next to that, we need to select type of analysis. Definitely this is an internal analysis, so we need to select internal flow through the object, and with the default setting on, we need to describe the geometry and flow. In CFD analysis, we need to have a closed geometry. In this case, we are having 5 different openings. All these openings should be capped, and initially we'll provide a cap at the inlets. Let us select cold inlet, and zone type will be velocity inlet or mass flow rate. We're keeping the name of this one as cap 1, that is the entry of cold water. Let us provide a cap at the cold water inlet. Cap 1 is made at the cold water inlet. Next to that, we need to provide cap at the hot water inlet. This case also zone type will be velocity inlet, and we are providing the name of this one as cap 2. Let us create cap at the hot water inlet. Cap 2 is also made. Let us see this one. Yeah, we have provided 2 caps. This is the cap 1 and this is cap 2. 2 caps have been provided at the inlet locations. Next to that, we have to provide caps at the exits. We're having 3 different exits: exit of cold water and exit of hot waters. These 3 different locations are there. Can show it by dragging. This is exit of cold water, and these are the exits of hot water, right? So we are selecting cold water outlet, and in this case zone type will be pressure outlet, and we're renaming this one as cap 3. Let us create cap at the exit of cold water. So we can see here cap 3 is also made. Next to that, we need to provide caps at the exit of hot waters. We'll select hot outlet 1, and in this case also zone type will be pressure outlet, and we are keeping the name of this one as cap 4. Let us create cap. Cap 4 is also made. Finally, we need to create cap at the exit of hot water 2, that is hot outlet 2, and again it will be pressure outlet, and we are keeping the name of this one as cap 5. Let us create the final cap. So all the caps have been created. Now our model is ready. We got a model with closed volume, and next to that we need to identify regions. That means the fluid domains should be identified. Here in this model we are having 2 fluid domains. One is hot fluid domain, another is cold fluid domain, right? So cap 1 is indicating the location of cold fluid entry. So at this location we have to provide cold fluid domain, right? And this can be done using different options like centroid of objects, or it may be numerical inputs or offset methods. We'll be using offset methods. You can see here the one diamond option is available. The location of this diamond will indicate the location of different fluid domains. So the diamond has to be moved a little bit inside to indicate the location of cold fluid domain or cold water domain, right? So what we'll do is we have to move this diamond a little bit inside. That will be done using y offset in the negative direction. Let us provide this one as minus 50. Minus 50 is very less. Let us move this one a little bit more, maybe minus 200. The amount has gone inside. You can see here with clipping planes. You can see here the amount has gone inside. That means it is indicating the location of cold water domain or cold fluid domain. Let us make this one a little bit inside more. We'll make this value is minus 500. You're fine. This is indicating cold fluid domain, right? And we can rename this one as cold fluid region. Let us update this region. Cold fluid region is identified. Next to that, we need to identify hot fluid domain, and that will be indicated with cap 2. By the same method what we followed before, we need to identify this one by offset method, and in this case the diamond has to move inside to indicate the location of hot fluid domain. In this case also, this diamond will move inside with the offset value of y. Let us provide y equal to minus 500. Enter. So it is showing the hot fluid domain. I can rename this one as hot fluid region. Cold and hot, two fluid regions have been identified. Next to that, we need to identify one void domain, which is needed to restrict the flow of fluid from inside to outside. We'll indicate any location which is outside this surface condenser domain. This is the location of diamond that to be moved outside this surface condenser. So we can locate this one by offset method, and it will be void domain. Let us rename this one as void region, and value of y should be very high. It will be in the positive of y. Let us put the offset value of y as 3500. It is outside this surface condenser, so this is indicating void domain. Let us update this region as void region. So we have created 3 different regions, excluding that one also. By default, solid domain will be created. That will be indicating the solid surfaces of this surface condenser. That is needed here in this case, as we are considering heat transfer analysis. Solid region also will be required. Fluid domains and solid domains are identified. Next to that, we need to define leakage threshold options. In our model, we don't have any kind of leakage, so we need to update this one with no leakage conditions. You can see here, these are the different regions obtained. We got cold fluid region, hot fluid region, and surface condenser, that is the solid one that is produced by default. We need to identify this one as solid. As it is a heat transfer analysis, we need to consider these boundaries of all the solid surfaces, and this is the void region. This one we need not consider. Now this one is indicating what type of meshing is required for different regions. For all the different zones, we are considering polyhexcore mesh. But in case of void domain, we need not mesh. We'll keep it separate. For all the cold, fluid and solid regions, we have identified polyhexcore mesh. With this one, let us update these regions. Next to that, with the default mesh control options, we can update this region. Finally, we need to generate surface mesh with the targeted skewness of 0.8. And again, from advanced options, we need to separate contact pairs. So it will be yes, and let us consider global minimum to be 5, and let us generate surface mesh. We can see that surface mesh is generated and different boundaries have been also created with the name of velocity inlet 1, 2, etc. Right? And different walls have also been created. These walls will be utilized for transferring heat by convection. We're having two velocity inlets, that is the inlet of cold water and hot water, and we're having three different outlets, that is one outlet for cold water and two outlets for hot water. Let us update these boundaries. Next to that, we need to add boundary layers. As the pipes are having very small diameter, so in this case what we'll do, we'll avoid boundary layers. With no boundary layer, we can update it. Next to that, we need to generate volume mesh with a quality improvement limit of 0.04. Let us generate volume mesh. You can see here volume mesh is generated, and while considering mesh type, we have considered tetragonal mesh for the solid region, and for two different fluid regions of cold and hot regions we have considered polyhexagonal mesh. Right, you can see here the solid surface is having tetragonal mesh, and the fluid domain, this is the hot fluid domain, which is having polyhexagonal mesh, and here in case of cold domain also we have considered polyhexagonal mesh. Right, and we can see the overall summary. Quality of mesh less than 0.1 is 65,531, and quality less than 0.04 is 25,209, and minimum quality is 0.015, and cell count is 1.38 million. You can see the mesh quality from here itself again. It is showing that minimum orthogonal quality is 1.5 into 10 to the minus 2. So with this mesh quality, let us move on to solution mode. While initiating solution mode, first of all we need to change the units, and we'll consider length to be in millimeter, and we'll consider temperature to be in degree centigrade. Let us close it. It is a steady state analysis, and we have to consider gravity. Direction of gravity will be y, as indicated by the green arrow here itself. This minus 9.81 meter per second square. Next to that, we need to select models. As it is a heat transfer problem, so energy equation should be on. And it will be capsule to turbulent model, realizable and scalable wall functions. Next, we need to consider materials, and we'll consider fluid as water that will be obtained from Fluent database. Let us consider water liquid, copy, and solid will be composed of copper, copy, close. So you can see here fluid we are considering water and solid will be copper. Next to that, we need to select cell zone conditions. That means we need to provide fluid domains and solid domains. Here in this case we are having two fluid domains, both will be containing water at different temperatures, but in fluid domains we'll be considering water only, and temperature will be provided during applications of boundary conditions. Let us consider cold water region. It will contain water. Apply and close. Similarly, hot water region that will also contain water. Apply and close. And the solid region is consisting of copper. Apply and close. Next to that, we need to consider operating conditions also. This is required to prevent backflow. And operating temperature, it will be 30 degrees centigrade. And we are considering specific operating density. Next to that, we need to apply boundary conditions. Here you can see we are having two different inlets, that is indicated by cap 1 and cap 2. From cap 1, we will provide cold water at normal temperature, and velocity we are considering as 0.01 meter per second. Temperature will be 30 degrees centigrade. Apply. From cap 2, we will provide heated water, that is the exhaust of turbine. It will be at a temperature of 100 degrees centigrade, and velocity will provide as 0.01 meter per second. And temperature, it will be 100 degrees centigrade. This is the exhaust from turbine, and that to be utilized to preheat the fresh water. Let us apply and close. We're having three different outputs, and all the outputs pressure will be equal to 0 gauge pressure. Apply, close. The remaining two exits also will be having same boundary conditions. It will be 0 gauge pressure. Apply, close. And finally, for the last exit, it will also have same gauge pressure as 0. Let us apply and close. We need to see the walls. We're having different walls. Let us see first inlet wall. It is also consisting of copper, and from this walls heat will be transferred by convection, and we are considering convective heat transfer coefficient to be 20 watt per meter square degree Kelvin at a temperature of 30 degrees centigrade. And wall thickness we are considering as 0.01 millimeter. Let us apply and close. Same boundary condition to be applied for the remaining walls. So what we'll do is we'll copy this boundary condition and that to be transferred to the remaining walls. Let us copy. So the boundary conditions are applied to all the walls. Let us close it. All the boundary conditions have been applied properly. Next to that, we need to select methods. And as it is a heat transfer problem, we are considering coupled method. And for special discretization, we are considering Green-Gauss node-based method. Pressure will be second order. Momentum is second order upwind. Turbulent kinetic energy is second order upwind. And turbulent dissipation rate also second order upwind. And finally, you can see energy also second order upwind. Next to that, we need to start initialization. And we're considering hybrid initialization. Let us initialize. You can see here hybrid initialization is done. Next to that, we need to start calculations. And in this case, we are considering 100 numbers of iterations. Let us calculate. Iterations have already started. Let the iterations move on. Whenever it is finished, we'll see the results and go for details analysis. You can see here calculation is complete. Now we can see our results, and results can be viewed from reports itself. Initially you want to see results from surface integrals, and you want to see temperature difference at the exits. So surface integrals, and report type it will be facet average, and you want to see temperature distribution. Cap 1, Cap 2, Cap 3, and Cap 4 and Cap 5. These are the different locations of exhaust and inlet. Cap 1 and Cap 2 represents inlet of cold water and hot water, and Cap 3, Cap 4, Cap 5 are the exit of cold water, and exit 1 and exit 2 of hot water. So we want to have temperature at different locations of these things. Let us compute. It is showing that temperature at the entry of cold water, it is 30 degrees centigrade, and temperature at the entry of hot water, it was 100 degrees centigrade. These two were defined by the boundary conditions, and the results at the exits we can see temperature at the exit of cold water is 64.70 degrees centigrade. Temperature at the exit of hot water 1 is 91 degrees centigrade, and temperature at the exit of hot water exit 2 is 89.04 degrees centigrade, right? So these are the results. We can see here that waste hot water has lost huge amount of heat, and its temperature has gone down from 100 degrees centigrade to 90 degrees centigrade approximately, and temperature of fresh water, that is cold normal water, has gained huge amount. Its temperature has risen from 30 degrees centigrade to 64.7 degrees centigrade, right? From here we'll see now pressure distribution and velocity distribution. Let us see first velocity distribution. Compute. Velocity at entry 1 and 2 is 0.001 meter per second, which was defined by the boundary conditions, and velocity at the defined exits of cold water and hot water is very less. All the velocities at the exits are same. It is 0.3097 meter per second, right? Pressure we need not see. Let us close it. Next to that, we want to see different contours of temperature and pressure, right? We'll see it from here. Contours, new contours. You want to see first temperature distribution. Let us see temperature distribution through surface condenser cold water region and hot water region. You can see here hot water region temperature is like indicated by different colors. Cold water, it is very less. At the entry of cold water, it is showing temperature is 29.7 degrees centigrade, and at the exit it is in the range of 43 to 57 degrees centigrade, which is indicated by blue color. And at the exit of hot water, its temperature is very high. It is in the range of 78 to 86 degrees centigrade. And at the right hand side, where the bent tubes are being shown, its temperature is in the range of 36 to 40 degrees centigrade, right? It is showing the temperature distribution at the cold water and hot water surfaces. Let us see the distribution through cold water region only. It is showing temperature distribution through cold water region. It is almost same throughout the cold water, only at the exit it is little bit higher, right? Next to that, we want to see temperature distribution through the hot water separately. Let us display. This is the temperature distribution through the hot water only, right? Let us see velocity distribution through this hot water. Velocity through this hot water display is almost same. It is not varying that much. Next to that, we want to see this velocity, pressure, temperature distribution through different planes, right? For that, we need to create a plane. Let us close it. We need to create two different planes, and from that two planes, we want to see velocity, pressure, and temperature distribution. Let us create some plane surfaces. One plane we are considering from YZ plane. Create. Another plane we want to create along XY. Two planes we have created, plane number 13 and 14. Through those different planes, we want to see this distribution. Contours of temperature, you want to see now new contour 2, and it will be temperature distribution through different planes of number 13 and 14. Let us see. It is showing temperature distribution through different planes. It's clearly understood that at the entry of cold water, temperature was 30 degrees centigrade. Temperature at the exit of cold water, it is in the range of 64 to 71 degrees centigrade. Similarly, entry of hot water was 100 degrees centigrade, and at two different exits of hot water, its temperature is in the range of 86 to 93 degrees centigrade, right? By the same time, we can see temperature through the pipes of cold water. It remains constant almost. And we can see that temperature through these pipes, it is in the range of 43 to 50 degrees centigrade approximately, which is given by the blue color region, right? Let us close it, and when you see pressure distribution, contours of pressure, when you see through these different planes. Let us display pressure distribution through these different planes. You can see here pressure through the cold water region, it is very less, but through the hot water, pressure is very high. Let us close it. Next to that, we are going to see dynamics of flow particles through this surface condenser. It will be obtained from path lines, new path lines, and we are going to see particle variables through the surface condenser, cold water and hot water region. Let us show it. You can see here dynamics of flow particles through this surface condenser. You can see the distribution of hot and cold water through different locations. This is showing dynamics of flow particles through the hot water region only. You can view it for cold water region also together. Let us see it. Dynamics of flow particles through hot water and cold water regions together. Let us display. It is showing the dynamics of flow particles throughout this whole surface condenser. It is clearly understood that at different regions, it is having different pressure and temperature distribution. You can see separately pressure and temperature distribution through these flow particles, right? You can see this one in the form of an animation also. That can be viewed from here, from pulse. Let us have a pulse. This is showing the dynamics of flow particles through this surface condenser. We can see temperature, velocity and pressure distribution of these flow particles through the surface condenser also. Okay, let us stop it. And let us close it. Next to that, we want to see some mesh distribution through the whole surface condenser. New mesh, and you will see through the faces only, through the faces of whole surface condenser. We don't want to see nodes and edges. Let us display. This is the faces of surface condenser. Next to that, we want to create a scene in between this mesh and also different pressure and temperature distribution separately. Right? Let us close it, and we want to create a scene. Let us have a scene in between the mesh and also different contours of pressure and temperature. Initially we'll see contour 1 and mesh, and the transparency of the mesh will be very high. We want to make the mesh to be transparent. Let us have a display of mesh and contour 1. Next to that, we want to see the distribution through mesh 1 and contour 2. Let us display. This is the scene between contour 2 and mesh 1. And finally, we want to see the distribution through mesh 1 and path lines. Let us display. So this is the scene between mesh and also that path lines. Right? You can see clearly. Let us close it. With this one, we'll conclude our today's CFD analysis of surface condenser. This is a very simple analysis. In this analysis, we have considered exhaust of turbine. This surface condenser is actually utilized in power plant. Waste from turbine is utilized to preheat fresh water. We could utilize the waste heat from the turbine, and in this case, we could increase the temperature of fresh water by a huge amount. Okay. Thank you so much for watching this video. Thank you again. Bye. If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.